Okay, so let us begin this lecture. So in the last few lectures, we discussed the one-point compactification of a non-compact and locally compact topological space. So let me make a remark on what happens when X is compact. So if X is compact, so in the results we proved we had assumed that X is not compact, but X is locally compact. But what happens when X is compact? So if X is compact, then X is also locally compact. This is because of silly reasons, as for each X in X, we can take the open set U to be X. Right. So remember the definition of a locally compact topological space. We need that every point small x in our space should have a neighborhood U such that the closure of U is compact. So if we take U to be X in this case, since U closure is then going to be X and X is compact, so this will do the job. So yeah, so a compact topological space is obviously locally compact, and if you consider the one-point compactification, of X, so we construct the one-point compactification in the same way. So our X hat is going to be X disjoint union one more point P naught, and the topology is given in the same way that we did in the non-compact case, and we can easily check that, and it is easily checked. That this point P naught will be an open and closed subset, right. So if our X is, for instance, the sphere, right, which we know is compact because it is closed and bounded inside R3. So then X hat will simply be the sphere disjoint union a point away from this. Yeah. So so the conclusion is that we have this inclusion of X into X hat, then I of X is not dense in X hat. So in any case, we wanted to compactify things so that we get a compact space, and so if our space is already compact, so then yeah, it's not very interesting. So this is just a remark. So in the previous lecture, we proved the following. So okay, so let me just make this P naught over here. Yeah, P naught is going to be this point. So so we had proved the following two results. A, let X, is everything okay? Yeah, okay. The first result we proved is let X be a non-compact and locally compact topological space. Then there exists a Hausdorff and compact topological space X hat and an inclusion I from X to X hat such that the following four things happened. X hat is simply I of X, disjoint union, one more point, P naught. I is continuous. I of X is open in X hat, and 4, I of X is dense in X hat. Right? So if X is already compact, so then everything else will happen, only the fourth condition will fail. And another result we had proved is the uniqueness of the one-point compactification. So let T, so let me just correct this. So I had in the previous lecture where we proved this result B, I had said that X has to be compact, but that's not necessary. So let T be a Hausdorff space. Okay. So I just want to correct this. So in the previous lecture, had stated this to be compact. Okay, so compactness is not required. We only need T to be a Hausdorff space. Okay, so assume that there is a continuous map J from X to T such that J of X is an open subset of T, and this map X J from X to J of X, it's bijective and is a homeomorphism. Right. So then we considered the following map. F from T to the one-point compactification of X. So X is a non-compact and locally compact topological space. So X, we have J over here, and we have X hat, this is our I, and we are going to define F as follows. So the picture we had made was the following. So we took this open disk, and let's say we put it into this closed disk, this J, right? And let's say I take an equator over here, so this is the one-point compactification, this is our additional point P naught, this is I. So this equator is going to look like something like this. Right? All the points at infinity, all these boundary points, like everything towards the boundary is going to get collapsed to P naught. Right? So as we move further and further away, as we move towards the boundary of this is our X, so all those points are going to get collapsed to P naught. Okay, so we define the map F as follows. Right? If T is in J of X, right? So then define F of T to be equal to I of J inverse T. this makes sense because J is a bijection from x to J of x. So if T is in J of x, then there's a unique J inverse T, and we can just apply I to it, okay. And if T does not belong to J of x, then define f of T to be equal to P naught, okay. And the assertion of our proposition was then f is continuous. Okay. So let us see some applications of this proposition. So this proposition we had proved in the previous lecture. So as an application, so let us prove that the one-point compactification is unique, right. So what do we mean by that? Suppose there are two compactifications so we have x over here, and here we have this inclusion I from x hat, I from x to x hat. Now suppose there is a j, yeah, from x to t such that we have the following properties: T is compact, 2 J of x contained in T is open, 3 T minus J of x is just one point. So let's call that point P infinity over here, or let's call it Q naught, just one point Q naught, and okay, 4 J from x to x, J of x is a homeomorphism. So in this case, T is another compact space which is obtained by adding one point to, it's another compact topological space, and T minus J of x is just this one point, and J and x is embedded inside T as an open subset. So then by our previous proposition, there is this map F. So we may write T as J of x disjoint union this point Q naught, and we may write x hat as I of x disjoint union this P naught, right. So by our construction definition of the map F, we have this map F, right. So here it is I compose J inverse, it's a bijection, and here it takes, there's just one point outside J of x, and that is sent to P naught, right, that's by definition, right. So this implies that clearly F is a bijective map, and by the previous result, by the previous proposition, F is continuous, right. Moreover, using the result, as T is compact, and x hat is Hausdorff, we get that F is a homeomorphism. Right. So here we have used the result. Use the following result. So F from x to y is a bijective continuous map where x is compact and y is Hausdorff. Right. So then F is a homeomorphism. Right. So let me make a remark. It is important that y should be Hausdorff. Important that Y is horsed off, right, which is an assumption throughout in the rest of this course, unless it is stated explicitly that a space may not be horsed off, because otherwise we can take the identity map from X to X, right, and give this X the trivial topology. Right. For instance, we can take X to be Sn. So here we can give X the usual topology, and here we can give X the trivial topology. Right. The identity map is obviously going to be continuous because here the target has the trivial topology, right? And but obviously this map is not horsed off. Even obviously this map is not a homeomorphism, even though X is compact, right? Okay. So before we proceed, let us remark that there is an important class of spaces which is not locally compact. Right. Many of the spaces we have encountered in this course, they are all subsets of Rn, and Rn is locally compact, and many of the spaces examples we have seen in this course are locally compact. Yeah, but there's a big collection of spaces which is not locally compact. So namely the infinite dimensional Hilbert spaces. Right. So let's see why this is, as an application of what we have learned, let's see why this is not locally compact. So if X is locally compact, so if you don't know what Hilbert spaces are, you can just forget about this example. So then there is an R positive such that the open ball, the closure of this ball of radius R around the origin, this those X in X such that the norm of X is less than or equal to R is compact, right? But this is not possible. Now, this is a compact metric. If this is compact, then this would be a compact metric space, and therefore every sequence would have a convergent subsequence, but this is not possible, as the sequence. So we can take these vectors EIs, the EIs form a orthonormal basis for this Hilbert space. REI does not have a convergent subsequence. Okay. Yeah. So this contradicts the result we proved, that every compact, the result we proved that every, in a compact metric space, every sequence has a convergent subsequence. So this brings us to an end of our discussion on locally compact topological spaces. So Next, we want to describe what the quotient topology is. So let's begin with a very an example from group theory, which you would be familiar with. So let G be a group, or rather a concept from group theory, and let N contained in G be a normal subgroup. Right. So then we have first we have the set G mod N, which is the set of equivalence classes G mod equivalence, where we define x comma y. X is defined equivalent to y, x and y are in G, if and only if y inverse x is in this normal subgroup. Right. So instead of writing G mod equivalence, we often write G mod N. Yeah. So moreover, we can give G mod N or G mod equivalence, whichever way you want to write it, a group structure such that the natural map, so let's call this pi. This is just a map of sets a priori to G mod equivalence, which takes an element x to its equivalence class. So in this case, the equivalence class is the coset of N. So this natural map, so we can give G mod N a group structure such that this natural map becomes a group homomorphism. That's one thing. Further, so that's one nice thing which happens when N is a normal subgroup. But there's another nice thing which happens. This map pi has the following property. If we have a group homomorphism, which is constant on equivalence classes, right? So then we get an induced map of sets G. So we have G to H, we have F, and F is constant on equivalence classes. So which means when we look at G mod equivalence, we get a map of sets, let's call it F bar, and the important thing is that F bar from G mod N to H is a group homomorphism. Okay. Note that since F is a group homomorphism, F is constant on equivalence classes, if and only if the normal subgroup N is contained in the kernel of F. So in the next lecture, we will see an analog of this concept for topological spaces. Okay, so before we end this lecture, let us see one very standard application of this corollary that we saw of the uniqueness of one-point compactification. So let x be equal to Rn, right? So then x is not compact and x is locally compact. Right. So now we know that. So recall the stereographic projection right. So what did we do? We had Rn and we took the sphere and we deleted the north pole, for instance, right, P, and for any point x on the sphere we joined P with x and we get a unique point y. So the stereographic projection phi is from Sn minus the north pole P to Rn, right, and we had seen that phi is a homeomorphism. Right. In particular, if we let T to be Sn and J to be equal to the inverse of this homeomorphism. So J is phi inverse from Rn to Sn, right. So then the hypothesis of the previous corollary, of this corollary, yeah, of the above corollary are satisfied, right, because we are taking T to be Sn minus the image of the stereographic projection is just the one point, the north pole, and this will imply that, this will force that the map from the induced map F that we get from Sn to x hat is a homeomorphism. Right. Thus, the one-point compactification of Rn is Sn. So we will end this lecture here.